Hello again. So today we are going to be doing another update video on the custom computer architecture design which I'm trying to build. So I haven't made an update video on this computer architecture in a while, and that's mainly because while I was last working on it, I was working on one of these boards like this. This is actually the computer that I had, or at least the part that I finished. And that was before all the wiring became really complex and it just increasingly became unmanageable to even deal with. So I kind of set that aside for a number of months until a few days ago when I bought a bunch of these breadboards and I completely rebuilt the entire thing, and I also changed around some components to make it simpler and just easier to deal with in general. So yeah, this is the schematic which I have of this which is built right now. Obviously, if you paid attention in the previous videos, I've shown the entire computer design as well as the emulator that I made for it. However, right now, all I really have is the clock, which goes to the program counter, which are these chips right here. Then there's a sub instruction count, I guess, to basically load registers during each clock cycle, or during each instruction you have to load the different registers to move data around, and that's handled by this chip right here. And then we have the address, which is going off this blue wire, and that's going to the ROM. Yeah, you can see right here, it's the ROM. And the ROM is actually a custom kind of ROM thing. Before, in the previous videos, I was attempting to use RAM chips for the ROM and just have a situation where I had to load the memory every time I turned the thing on, which would be very annoying to deal with. So I have opted for a kind of simpler design where I basically just have a decoder, and that's these two chips right here. These are both 3x8 line decoders, so I have to use two of them with an inverter tied to the enable pin. So for 0 to 8, or for 0 to 7, this one's on, and for 8 to 15, this one's on. But essentially I've simplified it into this. And then these are just tied to OR gates for each different instruction. I could actually show you the program that it's running, or that's encoded into the ROM. So it's basically just this add to number program. So yeah, it's 100110001 yeah, all that. Basically what it's doing is, well, I went over this program before, but basically what it's doing is it's inputting a number to the input register and that's storing it in the accumulator. And then we're going to store whatever's in the accumulator. So we're going to store this into address 1, and then we're going to input another number into the accumulator, and then we're going to add what's in the accumulator. So we're going to add this to what's in address 1. So we're going to add this to this, and then we're going to output that, and then we're going to branch to 0. So we're going to loop over again, and that's what it does. So yeah, that program is basically encoded into the ROM via these diodes, which are functioning as the OR gates. And then I also have a bunch of these transistors here. These are just to drive the LEDs, because I have a lot of LEDs and they kind of consume a bit of current. So I'm trying to alleviate that by passing everything through transistors to buffer it. Then from there, the ROM is going to give us data and instructions. So the instructions have to go to the instruction decoder. So that falls down here. So we actually decode the instructions, and we can find out which instruction we have to do. These are just the same instructions that it has: halt, add, subtract, stow, load, branch, conditional branch if 0, load value, input, output, and or not. And then we have the data, and that all it does right now is it goes back up to the program counter. So if we want to branch to an address, the branch will say okay branch, and it's going to tell the program counter to load from the data bus. Though the data bus is also used in my design for just an operand in certain instructions, load value. It's used to load just to load a number in that case, and also as a RAM address if we want to address the RAM instead of the ROM. So yeah, that's what it does. But right now it just goes to the program counter. Like as I mentioned, this is all that I have right now. It's missing a lot of stuff, including a bunch of registers and the RAM chip, as well as the ALU. The only instruction that this thing really has right now is unconditional branch, and that just kind of because I connected the unconditional branch, which is B. I've connected that to this inverter because in order to branch, it wants it inverted. Just how these counters work. So that goes up here and it tells it to branch. Yeah, so now I've actually turned it on and I've turned off the light so you can see it better. It's going to go through the program that it has. So you can see the program that's executing right now. So it's going input, stow, input, add, output, branch, input, stow, input, add, output, branch, and then it goes back to 0. So that's what it's doing right now. And as I said, the only instruction that it's actually executing is branch. That's helpful so it doesn't count all the way up to 215. So for example, if I take this out, now it can't branch, so it's gonna get confused and it's going to just count all the way up, so it's gonna stay on halt because it doesn't know what to do because the ROM is blank for that. So if I plug it back in, it's going to actually execute the branch instruction. So yeah, that's what it does right now. Also, you can see up here on these LEDs, this is the ROM address, so this is the current address. You can see it goes, these are the sub instructions. So yeah, it goes 1 2 3 4 1 2 3 4 1 2 3 4, and then it counts up on the actual address, which is these 4 LEDs. So 1 2 3 4 5 1 2 3 4 5 0 1 2 3 4 5, and it branches back to 0. And then here's the opcode that's used by the instruction decoder, which makes them much more readable, so I don't want to look at that very much. And then here's the data, and the only thing it shows is 1 very briefly, and this is going to be the RAM address which we're going to store the first operand in. So we're going to, as I mentioned, how the program works is we have to input a number into the input register, and that would store it in the accumulator. So we can only store 1 number in the accumulator, so if we want to add 2 numbers together, one of them has to be stored in RAM, and it's going to be stored in address 1. As I said, the data bus is used as a RAM address. But right now it's doing nothing. So yeah, so right now what I really have to do is try to implement the ALU and some of the registers to actually get it to do something or execute the most basic program that it has. Yeah, so right now I just kind of have the all the instructions going down here. I'm working on some circuitry to implement each instruction. Right now I'm mostly just focusing on implementing well, input, add, output, and stow. So we're gonna need the RAM for that, as well as the ALU. Though for it to be an actual computer, it's going to need the conditional branch in order to make it Turing complete, I guess. Though I think some of these other instructions would also be necessary. I'm not sure what exactly makes it Turing complete other than conditional branch. Uh, Obviously, if you only had conditional branch, stow, and add, that's not very useful. So you probably need some of this other stuff too, like subtract, um, and or not. So yeah, right now I'm just kind of waiting on getting some 4-bit adder ICs to help me actually implement it. So yeah, this is the update on my custom computer architecture. I hope you enjoyed this video and thank you for watching.